So is this going away? No, this is maybe disappear a minute. So our first speaker is Etienne Boursier. He's a researcher at INRIA Paris-Saclay. So his field of interest is, among other things, the theoretical understanding of neural networks. So Etienne, the floor is yours.
So I apologize for the delay. It's a bit on me because I wanted to show you some fancy animations. So I hope you'll enjoy them. So I'm going to present some recent work on the early alignment phenomenon and what are its consequences when you're training neural networks. So this was joint work with Nicolas Flammarion and Lucas Leovivia. So this is a project that started while I was at EPFL as a postdoc, and I left EPFL a few months ago. And so here it is. So here are the main questions that we have when studying the training of neural networks. So first, does the loss converge to zero, in particular when we are overparameterized so that we can actually reach zero? So this is, as Aurélien said earlier, it's very hard in the general case of neural networks because then we have non-convex losses. And so it's very intricate to analyze. Another question is the one of generalization. So in particular, even if you don't regularize explicitly your training objective, you still end up having some simple solutions in the end that do generalize well. And so this is also another interesting phenomenon that is intricate to understand. And all of this is also linked by the question of the role of initialization, so that I'm going to detail in the following. And so here the initialization plays some role because we are in a non-convex landscape. If you are optimizing on a convex landscape, of course, where you end up doesn't depend on your initial point. So as a disclaimer in this talk, I'm just going to focus on 2 layers neural networks because I would need to do theory on them. I'm going to focus on leaky value activation and on gradient flow, which was the continuous version that Aurélien introduced before, but without noise in my case. So here's the setting. So we have n training points. So here we're in a Euclidean structure as well. And our prediction function is given by some 2-layer neural network with one layer, one leaky value layer activation. So here I don't add any bias terms, but if you want, you can include them at least in the first layer to add by adding a 1 coordinate to the x. So if you add the last 1 coordinate to your x's, it's like adding some bias term in your intermediate layer. And so that's what I'm going to do actually in the following. So what we do is that when we train our network, we do some gradient descent or stochastic gradient descent. And to simplify the analysis, then I study the gradient flow. But here I have leaky value activation, which are non-differentiable at 0. So instead, I need to study the subgradient flow. So by considering the Clark subdifferential of my loss. And here my loss is given by the empirical loss for either the square loss or the cross entropy loss with binary labels, so covering both regression and classification. So the challenge here, so one of the challenge here is that we have a non-continuous ODE. In particular, we have a non-unique solution of this subdifferential inclusion. So this requires a very careful analysis, but it's still easier to analyze than GD with a finite step size. So let's first talk about the role of initialization. So the first known convergence result is due to several people in the field, including Jaco and Du. And so the main point was with a classical Gaussian initialization. Then if we have enough neurons in our network, then with high probability, our loss will decay exponentially fast to 0. So it's good, meaning that we have a loss that a training loss that converges to 0 at a very quick pace. But the thing is that actually this corresponds to a bad initialization regime. So why is that? Is that because we are in what we call the lazy regime. So this is something that was pointed out by Shiza a few years back. And so it said, okay, let's say we initialize our neurons with some scale that depends on the number of neurons m. And he says we're in the lazy regime when, so this scale lambda m squared times m tends to infinity when m tends to infinity. Because in that case, what happens is that if you take M large enough, you can show that actually where you will end up at the end of training is not so far from where you started your training procedure, meaning that you almost didn't change your parameters in the training process. And that is because actually the model behaves as its linearization around its origin. And so you're almost solving a linear regression with the random features that are given by your initialization. And so you're not really learning any new features. And so it can lead to very bad generalization properties, and it also poorly describes what happened in practice. So for example, if we take a look at this, so here is the first cool animation I have. So, so this is the kind of animation I'm using for the following of the talk. So the green dots correspond to data points. So here, as I said, I'm in R2 because you can add a one coordinate to your point that corresponds to the bias term in the network. So the green line corresponds to the estimated function at each time of the training. And each blue star corresponds to a single neuron. So a single neuron where, so its X value corresponds to the kink. So here I'm with a ReLU activation. So gamma is 0. So each X value of each star corresponds to the position of the kink of the associated ReLU. And its Y value corresponds to its out, so to its norm somehow. And plus or minus depending on the sign of the output value associated to this neuron. And so if we look at what happened when we train our network in this kind of lazy regime initialization, is that we quickly converges to some to training loss 0. But what happens is that it's a weird function that we end up with. And also we see that all the blue stars didn't move that much from the initial point. So that's exactly what I told you before, is that we do not move much from the initial point, and we have no guarantee on how simple is our function after training. So what I'm going to focus on now is what we call the rich regime, which corresponds to this kind of scaling. So lambda m is lambda divided by square root of n. So we are not in the converge. So if I recall what was before the lazy regime was lambda m squared times m goes to infinity. So here we're really at the limit of that just before. And here we even take lambda very small but independent of m. Also, to simplify the analysis, I'm going to consider what we call the balanced initialization, meaning that the initial value, the absolute value at initialization of my output layer is larger than the norm of the associated neuron, intermediate neuron. And why do I need that? It's to simplify the theoretical analysis, because we can show that actually this difference stays constant during training. And so a good point from this kind of initialization is that the sign of the output layer stays constant. So for example, we can get that during an initialization where the value is uniform on some ball and AI is either plus or minus lambda m with uniform probability. So the rich regime, it's harder to analyze because we have no clear global convergence guarantee as we had in the lazy regime. But we believe that it yields some implicit bias. So we have already some evidence that it yields implicit bias towards simple solutions. But so we need to understand all of that. And the thing is that we, even in the regression, our belief is that right now, to understand it, it's very hard and we can't really know how. And so sometimes we just need to understand the full training dynamics. And so in this talk, I'm gonna mostly focus on describing the full training dynamics, or at least the early stage training dynamics. So let's take the same example as before, but now in the rich regime initialization. So now you see that all the neurons are initialized near 0 in norm. And so, of course, our estimated function is close to 0 as well. And so in that case, what happens is that we have a much slower convergence to 0 training loss. But in that case, we'll see that the neurons significantly move from their initial point. So here you all see them moving. And at the end, we also have some simple estimator in the sense that actually we have a very small number of kinks. Okay, so here you see that actually our network is almost equivalent to having 3 or 4 neurons actually. And so it's a very simple network in the sense that it could be represented only with a width 4 network. So, yeah.
Is there any theoretical result saying that this number of kinks is better for generalization, or is it just like a...
Not really. But you know, there are some, I guess you know, that there are some guarantees when you have a small F1 norm. And so there were some recent papers, including one of mine, that linked related like small F1 norm to a small number of kinks, but that's not something we understand in general. It was only for the univariate case that we are mostly able to. And it's not even always the case. But you still, yeah, if you minimize your F1 norm, you can still show that you have some sparsity in the number of kinks, but at what point, at what level, it is not totally understood right now. Yeah.
Just a question for a person who are completely outside of the field. What do you mean by simple solution? What do you search? Why do you search simple solution?
Yeah, that's the thing. We don't really know. But yeah, it's mostly related to generalization because we hope that such simple solution generalize better to real world data sets. But the thing is that for generalization, you need to assume something on how your data is generated in the end, because I mean, simple can be many different definitions depending on what you call simple. It could be smooth, while here it is not at all. Here you have like almost non-differentiability of your estimator. So what I call simple is having a few number of kinks, and meaning that you could be represented by a small width network. Okay, but yeah, it's not so clear what should be simple in real life. But our belief is that it's related to having good generalization performance in a real world data set. Okay, so now I'm going to talk about the main part and the main novelty of this work is about the early alignment phenomenon. So if we look at the subdifferential inclusion that we had for our raw parameter, but now we look at it for each individual neuron, we have the following ODE, or differential inclusion. So meaning that we have our W that is in some set that is given by the Clark subdifferential again of the value. So here it's a Clark subdifferential of the value at Z. And also sometimes I'm just going to focus on the mean norm subgradient, meaning the element in this set is the minimal norm because it is the one that plays a key role actually in the dynamics. And so an interesting thing is that this set, and so somehow your gradient depends only on your estimated function at time t and the activation of your neuron W. So what I call by the activation is with which data points xk your what is the sign of your scalar product with this point. So either it's 0 if you're orthogonal to this point, or -1 or +1, depending on the sign of your scalar product. And so an interesting thing is that you have like some vector fields that gives you the movement in some cones. So the cones corresponding to what we call also sector. And so a cone is a cone of constant activation. And so in that, you can understand easily the movement. So if now I define, I rescale actually my neuron by AI so that it's in the unit ball. What I have is this new equation. And so the main interesting from these two equations is that the first one, it scales in a big O1 or a big theta 1. So meaning that it is at some constant scale. While the other one scales with the norm of Wi, which I recall is bounded by AI. And so at initialization in particular, it's very small because I take lambda very small. And so an interesting thing is that the directional movement given by the first equation will happen in a time that is big O1 because it will happen quite quickly. While on the other hand, the neurons norms need a very long time to grow in a significant amount. And so because the neurons norm actually do not move that much during this time, during this phase, what we can say is that our estimated function is nearly 0 during this whole neuron movement phase. Okay, and so when we approximate our estimated function as 0 during this whole neuron alignment phase, what will happen is that we have the following equation on our directional neurons. And so what is interesting now is that it's much easier to describe because it is just the projected gradient ascent or descent depending on the sign of A on the unit ball for the continuous function G given as follows. So just like the scalar product of W with the mean norm element of the Clarkson differential I told you about. But here the thing is that here it's 0, while before it should have depended on theta t, but we can approximate it like that. And so from there, the main idea of the early alignment phase is that the neuron's weight will align towards a few key directions and the sparsity in the number of kinks of our function at the end that are given by the critical points of G. So now I'm going to say that the vector dw is extremal if, so we have the equality, so between our F activation, and roughly just said that this corresponds to a critical value of G up to scaling in norm. And so this this is what I call the early alignment phenomenon. So it has been already described in some works to describe the early dynamics, but it was always specified to some very precise examples. More generally, some people, including Maynard, described it, but in a very qualitative way a few years back. But until now, we have no general rigorous quantitative description of this phenomenon. And this is our goal in this work. Okay, so here is our assumption that is pretty mild. So we just assume that our points are generated from a continuous distribution. So we avoid some degenerate cases that could happen. And also we say in the following that a neuron G is well conditioned. So if two things, so if first, it's a scalar product with, so you can see its scalar product with the gradient in its vector field at initialization is positive. And so some weird second condition that just means that roughly you do not spontaneously leave some manifold if you're in it. Because what could happen, can I use the blackboard quickly? So what can happen if I take the okay. If I take the OD, for example, so okay, let's do a very basic one. Is equal to 1. If I take a look at this OD, which is a non-continuous one, that is close to actually what we have when we take a review activation. We have like that all the solutions of it are of the form C minus T plus 4 T. Okay, so that's important anyway, you can see. But the idea is that you have many solutions to this OD, and they include every ramp that starts at any point, and they could even never start and only start at infinity. And so we said that roughly a neuron is well conditioned if among all these solutions it corresponds to the one where C is infinity. And so meaning that you don't have a ramp, but it just stays flat to 0. So yeah. Initial condition at 0 is 0. And so this is kind of hard to understand the second condition, but it just says something like that. Like if you can stay in your manifold, you won't spontaneously leave it just to annoy me. And so here's the main result that we have. So we have that for any small constant epsilon, if our initialization scale is small enough, then for some time tau, that scales logarithmically with 1 over lambda, we have two things. So the first one is that after this time tau, the neuron norms didn't change significantly from the initialization. And the other one, so this holds for any neuron, and the other one only holds for well-conditioned neurons. And it says that after this time tau, there will be all nearly aligned with some extremal vector of your function G. And so you will be aligned up to some term scaling in lambda. So polynomially in lambda. And one of the things here is that lambda star does not scale in M, but only on the data and epsilon. So that's, as I said, like after this early alignment phase, what time does it? Okay. After this alignment phase, you will be only aligned with a few key directions, meaning that you have some sparsity already in the number of directions that you're representing with your network. About the well condition assumption or requirement, is that I actually needed to avoid intricate situations that would happen around saddle points of G. And so the conditions 1 and 2 in the well condition thing imply actually that the neuron stays on critical manifolds even in around saddle points when it encounters them. So actually it does not escape saddle points, but it stays on them, as I explained, because of this thing actually. And also, if we didn't have that, finite time bounds would not be possible, because otherwise they could just stay around your saddle point some indefinite time that could even be infinite, and then they could just leave them at some point. And so you wouldn't be able to control them up to a finite time talk. And so if I don't have any saddle point, I can actually have a much stronger theorem that says that for any neuron J satisfying that it is not aligned, but in the other way around, with its initial vector field at initialization, then I can have this. So meaning that I can actually include almost all the vectors, all the neurons J in this condition. So here's the illustration. So on the case I already showed you before, in the rich regime. So now I also had another type of animation. So here it's a polar coordinate visualization of my neurons. So each neuron corresponds to one of the stars. So being red if it's positive A, and purple if it's negative A. And so here it's positioned around the circle, give you the directional position given actually by the real scale W. And the radius is just corresponds to the norm of your neuron. So it's really great to visualize this early alignment phase. Oops. Because you see that at the beginning, so these neurons, they don't move from zero, actually, they just move in direction. And so we see that after the initial phase, only a few key directions remain and are represented by my neuron. And after that, I have a growth in neurons that is even harder to control and to describe, so I'm not going to discuss about that. Yeah. So as I said, one of the main benefits is that we have some implicit regularization, because then we will end up with a very few number of kinks represented by our function, or equivalently, meaning that our final network can be represented with a small width network. So I'm going to illustrate that on the orthogonal example. So if we take now our data set such that the inputs are orthogonal, so even orthonormal, but it's just the orthogonal condition that is needed, and a radio activation with the square law, then I am going to be able to describe everything about the trajectory. And so here, this approximates the high dimensional setting where the dimension is much larger than the number of points there is in the data set. And what is nice with this assumption is that you can describe everything in full detail. And so here again, if we assume that we have a small enough scale of initialization and that we have a large enough number of neurons, then with high probability, the gradient flow converges to some interpolator of my data, meaning that the training loss is 0. And moreover, this interpolator minimizes the equivalent norm of the parameters. So actually, we can show that it is equivalent to minimizing the F1 norm, meaning that you have some generalization property that holds for this kind of network. So from this result, you have two good things. It's first, you converge to zero training loss, but also you have some implicit bias towards minimal norm interpolator, which happens to have good generalization properties. And actually, when showing this result, we can describe the full dynamics, where, of course, first we still have this early alignment phase, so it's good that we can use it again. And then we will have other movements that I'm not going to go into the details, but just show you on these plots. So here I'm considering orthogonal data points with 2 points, because I don't know how to represent data in higher dimensions. And so is what happens. And in that case, it's still describing perfectly what happens. So first, we have the early alignment phase. So all the neurons will either align their king position on the right or on the left, corresponding to one or two, so to one of the two key directions. And after that, we will have a first growth phase So where one of the neuron will of the data point will be learned, and actually one of the neuron of the final estimator. And after the second phase, we have a third one where the same happened, but for the other point. And then we don't move anymore from this representation. And so we see that at the end, we have a network that is just represented by two kinks, one that fits actually all the, so if you were in more than 2 points, you would still have two kinks, one that fits all the positive labels points and one that fits all the negative labels points. Okay, so this was about what is good from this early alignment is that we have some nice implicit regularization and some sparsity in the number of kinks, but you also have some drawbacks. And the main one being that it's hard to actually reach global minima for training loss with this. So for that, I'm going to show you some counter example of convergence towards zero training loss. So if I take the 3 following points in R2, so I could move them a little bit, but anyway, as long as I have this, I will be able to show you that it doesn't work. And so here my points again, I have a one coordinate on the second dimension to include the bias terms. And so what is important about these points is actually that they are all positively correlated. All my labels are 0. And actually the third point is that the linear regression actually is below the extreme points of these 2 points. So this is also an important thing actually. And so what is the consequence of this property is that we first have only a single extremal vector D that is given by the sector where you are positively correlated to all the training data. And so in that case, we can show the following, that if our scale of initialization is small enough, then the gradient flow will converge for any M to actually the linear regression. So yeah, I need at least M to be large enough because otherwise I just have no neuron. But if M is large enough, then I will just converge towards the linear regressor of my data. And so an important thing is that first, my training loss is not 0, while I could obviously have a 0 if I reach the global optima. And an important thing as well is that lambda star does not depend on M. So I'm going to discuss about that later. And as I say, it's not, it actually holds for a non-zero measure data set. But it's not a totally degenerate counterexample. So as I said, lambda star does not depend on M, meaning that I can even have non-convergence to global minima for M going to infinity or even M being infinity. And so this somehow contradicts a result by Lena Ishida and Francis Bach from 5 years ago that said that if you are in this regime and you take your number of neurons going to infinity, then at the end of training, if you converge, so here we converge, so actually it's really in this setting, your training loss will be 0. But actually the main difference with their result is that they need smooth activation. While here we abuse actually the fact that we have non-smooth activation given by the value activation. And the thing is that this smoothness, it's what allows you to preserve the omnidirectionality of the neurons, meaning that your neurons at any time of training will cover all the possible directions. While in our case, you saw that what happens is that quickly we only have a few key directions left in our neurons. And actually, this omnidirectionality is totally essential to prove the global convergence of your estimator. And so what actually happened with this 3 points example is that in the first stage, so here again, we have the early alignment. So recall that we have a single extremal vector, meaning that all the positive, okay, so purple are the positive A, all the positive neurons will align towards these extremal vectors. Meanwhile, all the negative neurons can do whatever. It's not a problem for us, actually. And after this phase, we have a growth of this cluster of neurons that were aligned towards our extremal vector. And so from this point, we are equivalent to the linear regression. And we can have some other neurons that are close to 0 in norm around. But actually, these neurons will never come up again. And we won't move from the linear regressor until the end. And so we could take M as large as possible. It would still be the case. And so we end up, that's what we end up with the linear regression. So in conclusion, small initialization leads to early alignment, to the early alignment phenomenon and phase, which has both benefits and drawbacks. So benefits being that you have some implicit regularization in your learned network. And the drawback being that it's much harder to optimize and to find global minima when you do that. So the question is ReLU or non-differentiable activation a problem, because that contradicts Shiza and Bach theorem. And it seems, for example, that preserving omnidirectionality is key to have a global convergence to 0. Thank you.
We have a few minutes for questions. Yes.
Two more questions. So first, what is the role of the parameter gamma in your ReLU?
Gamma doesn't play that much. Actually, I wrote the result with gamma equals 0 at first.
You don't need
Yeah, it was just to be more general. I included the leaky activation, but actually I first wrote it with gamma equals 0.
the second question about I meant, like what role does the data distribution play? Because I imagine that it's implicit bias for in sparse network will depend on the data distribution, because if your target is very complex, you have a lot of, let's say, data in that with many components, generalization will be bad.
Yeah. Yes. Yeah, that's what I said. We hope that it seems that naturally, yeah, like for example, in general, you will assume that your data distribution is given by a teacher network or something like that, and in that case, it's obviously good because what I call simple is having a small number of kinks or a small width network, so you're somehow optimizing with a good norm corresponding to your data distribution. But yeah, if it's something totally different than having a teacher network, yeah, then you might have very bad generalization.
For a very complex teacher.
Yeah.
So about the ReLU, like in practice, nobody uses smooth activation, right? So everybody uses like that kind of stuff. So maybe the question is, maybe convergence to global 0 is not a big deal.
Yeah.
Can we rephrase the question? I mean, your question is like ReLU is a problem because that it looks like essential.
Yeah.
Like it's only directionality. Or can we form the question as maybe converging to global 0, like the 0 loss is not a big deal, and also we can just use, I don't know.
Yeah. But okay, we could discuss about that. But the thing is that, okay, yeah, as you said, we don't exactly use ReLU anymore in practice.
No, like the small ones, people don't use it. Like, nobody uses 10H, sigmoid.
Yeah. So everyone is using ReLU.
Yeah,
okay, yeah.
So like ReLU seems to be like a good thing, but you're kind of saying like a negative result, saying it's not going to converge.
Okay, so it's a bad thing in theory. In practice, it's different. My belief is actually that if you take, because what happens about the no convergence result is that you need actually lambda to be very small. And my hope is that for intermediate values of lambda, then you will still have something coming on from the implicit regularization side, but not this bad convergence thing happening. But in theory, it's very hard to analyze intermediate scale stuff. So yeah.
How much, let's say, technical hassle does it, additional technical hassle does it bring the fact that ReLU is not differentiable in 0 with respect to the case where it would actually be fully smooth?
A lot. So okay, the thing is that you need actually, for having this early alignment phase, you need to be homogeneous, to have a homogeneous activation. And so what is a homogeneous activation? It's any leaky ReLU. And so it can be, so to be continuous, it needs to be the identity. So actually, at first, to have the early alignment, you need this homogeneity because all of the rescaling stuff and things work. But yeah, so then you're non-smooth, and then it adds a lot of difficulty because you have, like, it's hard to say, but because you have because you have to be careful about sub-differential about Clark sub-differential and stuff like that. But if you assume, for example, population loss, then you are differentiable again.
If you assume what?
Different population loss, meaning that your data set is infinite and it gives the full space. Then in that case, your loss is differentiable again, except at 0, but you never go to 0. But then you will still have struggles with saddle points of your G function. So
But, okay, so I understand that this homogeneity is important, but
Yeah.
if you would like modify a value with a very small epsilon, you would have smoothness and you would have still the fact that you technically homogeneous, you would like have some correct picture, maybe that, I mean, of course, then you would have the problem that.
But the thing is that actually here we're taking everything go to 0. And so even if you have a small smooth bump around 0, there might be possible that actually you will be even closer to 0 than, and so you will be before this bump. And so around the non-homogeneous part of your function.
We have time for one more quick question. Yeah.
Technically possible to generalize to deeper levels.
It's hard to say because what we have with deep networks, so deep to me means strictly more than 2 layers, is that yeah, we don't we can't just study each neuron individually. Like you have some intricate dynamics happening between the neurons, and so it's much harder because here you just have to look at every you can look at every neuron individually, and it's much easier. And so you have like some mean field regime somehow, and so yeah, if you are in deep network, you don't have that anymore. Or I guess maybe you have, but it's not that known.
Okay, so very good. I think we're just going to stop here. We have 12 minutes of break, so a little bit less than we intended, but let's come back on time so we can stick to the schedule. Thank you very much again to the speaker.
So the next is why you already very nice talk.
Yeah, thank you. It was good.
Donc, quand tu sais tes données initialement, dans un même paquet, les files,
How are you?
Hi, nice to meet you, Marcel. Yeah.
I have a question. So who is in my session that I'm chairing? Because I think there's a mismatch between the list and the exact.
When is your set like?
At the next one, but like
I think the updated schedule, I mean, perhaps, oh, the session